Alright, so we'll go ahead and get started. First thing I wanted to mention, the next homework is posted. What we're going to do is we're going to do a little bit of scraping from this website, Hacker News, which is a website full of interesting sort of tech and programming stories, and also some of the worst opinions you'll see on the internet. So if you look at the comments for any sort of controversial story, you'll see some just really awful takes. Our job is basically, if you want to be a successful startup, and one really helpful step on your way to success is to get your company front page in Hacker News. So we're going to try to perform some analysis to figure out if we can figure out how to do that. Okay. So basically, you're going to scrape a few pages worth of and the input that are closer, that are within a distance R. So this, we might do something like this, where we want to we care about the actual location of the points as opposed to the nearest points, which might actually be pretty far away. Okay. And then the other query we're interested in is the Knn Query, which again we take a point P. This time we take a number K, right? And here I get the K closest points. Cool. So we have points. These could be in any dimension. Okay. So we talked a little bit yesterday about the 1D case. We'll talk a lot about the 2D case because it's nice and easy to draw, and it's a lot more interesting and challenging than the 1D case. But we'll also talk about what happens if I have 3D data or 10D data or whatever else. So these are basically these are the operations we want to support. This one, pretty obvious why we care about this one. This one, I imagine you could see uses for this as well. If I can do one of these, I can do like a pretty dumb hack to compute the other without too much fuss. Right? So let's say I can do a range query. I've written the code to do this somehow. I could use this to implement KNN without too much fuss. So how would I do that?
Try an arbitrary distance, then try again to get the right number.
Yeah, I basically pick an R, and then I just grow it until I get at least K things back. Right? So that's maybe not the most efficient. I have to do multiple queries maybe, but easy to do. Or if I do this, right, I pick an arbitrary K, I increase it until at least one of the elements I get back is further than R away, and then I know I can stop. So it's pretty easy to go back and forth between these, but each of them are more efficient if I, kind of directly shoot for what it is that I want. Okay. So maybe we'll start with the kind of simplest data structure that I could use for this, which is no data structure. And so I have my my input points. So if I just store that as an array, okay, and let's maybe do the range query first. So how would I go about implementing this? Just have a gigantic array of points. I need all the ones that are closer. Yeah, so I wouldn't call it a search, but I could look at all the points and yeah. So I could do like a for loop and like an append. I'm going to do like the clever Python thing. And I'll just say, what I want to do is I want to filter. I'll write it out as in kind of a Python syntax. So for each of my points Q, if the length of, the way I can compute the distance between points, I can subtract them and then look at the length of what I get back. And then if that's less than R, and I keep it, otherwise I throw it away. And so filter basically does for each point, if this is true, keep it, otherwise throw it away. So pretty simple algorithm, right? I just look at all the points and keep the ones that are close enough. Cool. Any questions about that? We've seen map before. We haven't really dealt with filter before, have we? So filter is it's in the same family as map. Instead of transforming every element, I just only keep the elements where this is true. So I pass in, I have like an array, I filter it with a function, and all the elements that the function is true for, I keep, and otherwise I throw them away. So this is the range query. very simple, right? It's a one-liner. What's the efficiency going to be of this, or the runtime? Yeah, so let's say I have endpoints. All right, this is going to be O of n because I have to look at all my points to see how they close. Okay. Let's look at the Knn query because it's going to be a little bit interesting. Any thoughts on how we're going to do this one?
Sort.
So we have to. So we could sort by what? Yeah. So I could do points. Sort by distance to p. So pseudocode. So if I sort all my points based on their distance to p, and then I return what? Like the first k sorted points. Cool. Okay. What's the runtime of this going to be? The n log n, right? Because I'm sorting endpoints. Okay. If k is like 1, does it seem like I could do better? It seems like I should be able to do better if k is small. Okay. In fact, sorting is probably doing a lot more work than we need to be done. Because I don't really care about sorting in this case. What is it that I care about?
Just finding the next number closest. Sorry.
Closest to.
I'm trying to think how to articulate it. Like, it could be arbitrary. So closest to the point that you're feeding.
I see. So if k is 1, right, I just need the closest. Yeah. And even if k is bigger than 1, sorting is still kind of doing more work than I need.
You can have a set number of slots available for that's k, and go through and find length of each one, and then just keep replacing the largest one by the smaller one.
So these are all my points. What I really want, or what I really need to do, is if I sort them, cool, like that will work. I have organized things how I want. But it's actually more than I need. What I really need is I need to put all of the points that are closer than the kth furthest away point in one area. All of the points that are farther away somewhere else. I don't really care what the order is of them. I just need to make sure that they're kind of split up correctly. And then, to kind of make sure I'm right, I want the kth farthest away one in the spot it would be if it were sorted. Does that kind of make sense? So as long as I get point k in the right spot, all the ones closer on the left, all the ones farther on the right, then I can still return this area, and I'll get all the points that are, closer than k. I could sort this if I wanted to. It may or may not matter. Right? But I don't care what the order of these points is at all. Right? They can be in whatever order. They could be backwards. Don't care, right? Because I'm not going to look at them. So sorting them is a little bit like overkill. Yeah.
Why do we care the case composition?
Because in order to know that all the ones that are further away are over here, we kind of have to know what they're being compared against. So it's not so much that I care this is in the right position. It's that to know what values need to be over here, I have to know what the kth one is.
Finding the kth one would be difficult.
It seems like that, but actually it's not that bad. So this is what's called computing an order statistic. So we talked about this as like finding the median or finding the 25th quartile or whatever. And there's actually an order n algorithm to do this. So in fact, actually we can, instead of using sorting, in C++ standard library, it's called nth element. You say basically, here's my list, put element k in the right spot, and then put all the smaller ones on one side, all the bigger ones on the other side. And that's actually a linear time thing. So we can actually do this. If we use the nth element, we can actually get this down to linear time, which is kind of a neat thing.
Can you say again what is it called to find the case?
So it's called the order statistic, is the general term for finding the, you're putting a particular element in the position it would be if it were sorted, and then you're putting the smaller elements on one side and the larger elements on the other. So yeah, the order statistic or nth element, the median is a special case of that. So yeah, we can shave off a log n factor, which is kind of nice. Still, we have to look at all the points to do either of these things. So not ideal, but still an interesting improvement. Again, I think I mentioned before, the algorithm for the order statistic is a really, really clever, cool algorithm. So if you get bored or want to do some interview prep, the algorithm for computing order statistics is really clever. Okay. Cool. So if we do no pre-processing, we can do our queries in order n time, which, okay, not great. Yeah. Questions about that? So it seems like probably if we do a little bit of work up front, we should be able to do our searches faster, right? And so that's what we're going to talk about for the rest of today. We talked a little bit yesterday about one technique, which is works really, really well if your data is kind of uniformly distributed, which is just splitting your data up into buckets and storing an array in each bucket, and then doing basically what we just did on a per bucket basis. Okay. So that's the idea. So we just split into buckets. So what would our bucket data structure? What would we have to store in here? Yeah, so we need to store basically the buckets. So if I stored my bucket as just an array of points, and I had this 2D example, what I might be storing is something like the bucket and a 2D array of buckets, right? Something like that. And then I also have to store a little bit of geometric information. Right? To know what buckets to put stuff in, I have to know about basically what the origin is and what the size of each, what the dimensions of my bucket are. And so I need to know corner position of my stuff, and then the size of the buckets. Cool. So maybe let's look at preprocess or like a constructor. What am I gonna? What am I gonna do in my constructor? So one thing I'm gonna do is like for each bucket, look at all the points and figure out which points should be in that bucket. Does that seem like a good idea? No? Good. What's a better idea? So, for each P in points, find the bucket that P should be in and insert it into that bucket. The runtime of this can be. So I'm doing, I'm looking at each point, so it's got to be at least order n. There's this stuff on the inside. Constant. So let's say insert. So let's look at the insert part first. So insert into a vector, that constant time operation. Trick question. Well, it has to be growable. So amortized, yes, it is constant. So if I do this a bunch of times, as long as I have a sensible growth strategy, right? If I like double my vector each time I have to resize it, then on average I expect to move each point one time. So it is constant. So that part's constant. Can I find the bucket quickly? How do I find out what bucket a point is in? So maybe let's just look at like one. Let's say at first I want to look at like what column my point is in. Okay, so this is my point P. I have to figure out what column it's in. How do I do that? I could like loop through all my columns and check.
Did you know the bucket size?
I know the bucket size. I know where the corner is. So close. I actually, modulo is a little overkill here. I'm dealing with floats, so modulo is probably not what I want. So what simple math operations can I do to figure out what column I'm in?
You do the size of each one.
So this is like an arbitrary thing, right? I kind of would like to get this. I'd like to know not the position here, but I'd like to kind of know the distance here. Right, so how do I get the distance from the corner? So subtract, right? So I'll take P minus corner. Okay, so that tells me this distance. Cool. And then how do I get the bucket number? And so this will tell me which bucket I'm in. Right? And this is a constant time thing. Right? So this is going to be an ON thing. And for each point, I do subtraction, division, and I answer. Or a few subtractions and divisions. But yeah. So I do a little bit of pre-processing. I look at all my points one time. Okay? And let's see if this can speed up my searches. So maybe let's look at the range query first. I know these buckets, I have this bucket data structure. I want to find all the points within a range. What I do? So the range query, if I look at it kind of graphically, basically it tells me, give me all the points in that circle or sphere or whatever. So what could I do?
Figure out what buckets are inside.
I want to find out which buckets overlap with the sphere.
And then go inside of each bucket and see what points are inside of that as well.
Yeah. So basically, I'm going to write out the pseudocode. The way that you actually implement this might, there's a few ways you might think about doing it, but basically, I find the buckets that overlap my sphere, right? And then I just look at all the points in all those buckets. Right, so for each point in any of those buckets, if they're close, I keep them in my list that I return. Right. So this, I needed like just high level thoughts about how you would actually find the buckets that overlap. So I could, if I know P, right, and I know R, I could compute kind of the square or the cube, right? And then it's really easy to do overlap between like cubes. So that's one thing I could do. Another thing I could do is I could look at the center and like subtract off the radius and see like where I get to and do something kind of like that. But yeah, that's kind of the basic idea. Cool. Yeah.
We're assuming here that the 2D size of the bucket is the same for all the buckets.
Mm-hmm.
Like they might not contain a single point.
Yes. Yep. Yeah. So these are evenly sized or evenly spaced buckets. Yep. And that's actually, so if I lose that, then finding the bucket becomes more difficult because I have to kind of like actually do a search. Yeah. So the fixed size buckets let me do division for searching, which is division is a very fast search. Right, so this is bucketing. Any thoughts on how we would do KNN? Can we do, like, does anybody see anything that's like obviously way better than doing kind of range queries of increasing radius?
K is small, just look in the bucket.
Yeah. Yeah, that's kind of the idea. You have to be a little bit more careful of that because let's say you put your point right here, then it actually may be that the closest point is in a neighboring bucket. But yeah, I kind of I think it makes sense to basically find the small neighborhood of maybe all of the buckets that are adjacent to the one it's in, search them, and then if you have to, kind of expand.
Look at the 9 around the 1.
Yep. Yeah. So yeah, whether or not you might be thinking in terms of like buckets instead of distance, but yeah, I don't know that you can do better than kind of just a expanding search. So yeah, this is a remarkably good data structure for data that is uniformly distributed. Any thoughts about why like this works better than something that's more complicated? Yeah, so we're splitting the problem up into smaller pieces. Yep. So that's definitely a good part. But the pieces might not be all that evenly divided, right? We might have some big arrays in some of these buckets. And even in those cases, it works pretty well. Caching. So this is a super cache-friendly algorithm because we have just arrays. We're reading through an array in order, right? We load our data into the cache line. We use every little bit of that cache line, right, in order. So this actually works really well just because it uses the cache really well. There's not much computation, right? We load the memory once in a very predictable way, and so this actually works pretty well in practice. Cool. So this is bucketing. This is one of the data structures we'll implement. Right. When our points aren't evenly distributed, right, it starts to look kind of like the no organization thing, right? If you have a bucket with 1 million points in it, then you didn't really win that much. So we'll look at one. I'm going to go a little out of order from the notes. We're going to look at a different type of bucketing that is adaptive. Okay, so it's bucketing, but we are going to be sensitive to the data that we have. Okay. So what's kind of maybe the simplest way we might break up our domain into buckets? We can either just like cut it in half, right? But since we have like X and Y together, cutting it into quarters so that we split along both directions is probably a helpful thing to do. Okay. So let's imagine we do this. Okay. All right, so I have 4 buckets. Okay. So like what we just did, but easier, I guess. Right? And let's say my data looks like this. If I had evenly spaced buckets, like what I just did, I'd be like wasting a bunch of those buckets, right? I'd have a bunch of buckets that were like empty, and I'd have stuff here that was like pretty full. Okay. So, right, as it stands, right, not a great way to organize my points. How can I improve it? Yeah.
But where you could set some sort of threshold and say, I want you to keep, quartering squares until they have, say, like 4 or 5 points inside of them.
Exactly.
So the ones on the outside aren't going to divide it.
So this bucket's too big, so I just split. And maybe this one's okay. This one might need to get split a few times. And now I have buckets that are all kind of pretty small numbers of points. But how do I find out which of these little buckets a point is in? Okay, so I want to do, when I do my query, I want to look for points around here. What do I do? I don't really have an easy way to like jump straight to this bucket. How do I find it? I mean, take a second to talk to your neighbor, think about how we could organize these buckets so that I can actually find the bucket that contains a point.
Yeah, it's like some kind of way to link in. So you have your initial ones, and then you get it and it's got yeah, and then you've got, so like the first one, these ones don't have anything else on
Alright, so the word I'm hearing is tree, which is good. So how can I organize these points in a tree, or these, sorry, how can I organize these buckets in a tree so that I can do searching efficiently? So what would a tree node contain?
Maybe the points.
So it could be points. So for these nodes, it would contain points. What about this square? Doesn't really make sense to contain points there. There's too many of them. So you'd have buckets. How many buckets are we going to need to split? 4. So this is a data structure called a quadtree because each node has 4 children, or each internal node has 4 children. So up here we have the root. Okay. I have children. We have the northeast, northwest, southeast, southwest. Okay. So I'm going to have 3 children that are now leaf nodes. Right? So my southwest, southeast, northeast buckets are just they're gonna be nodes that are just gonna have a list of points. So here, just have a list. Okay. And then my northwest is gonna have so it's not a bucket of buckets. It's a node whose eventual children will have buckets. So here we have this node here corresponds to this rectangle, or sorry, this square. Right? It also has 4 children. So this one, the northeast and northwest, these are leaf nodes, right? They just have lists. Southeast and southwest are internal nodes, so they also have children. So my southwest node, these are all leaves, right? So each one of these is just going to be a list. Okay. My southeast, its children, 3 of its children are internal nodes. 1 is a leaf node that has a list, right, and so on. So this is our data structure. This is called a quadtree in 2 dimensions. In 3D, what do you suppose it's called? An octree, because each child, I'm going to have 8 cubes. Each cube gets split into 8 cubes. This is the octree. So beyond that, people don't really use these because how does the number of children relate to the number of dimensions? It's 2 to the number of dimensions. So beyond dimension 3, I start to have way, way, way too many children. And so basically people don't use these for very high dimensional data. In general, the problem is called the curse of dimensionality. For a whole bunch of algorithms and data structures, very often the dimension is an exponent in either the size or the runtime or something. And so as the dimension grows, they become impractical really fast. Okay. So quad trees and oct trees get used a lot. The 16 tree does not get used. The 32 tree I've never ever heard of. So these are the ones people use. Okay. Let's talk about how we build one of these. So first, let's talk about our node struct. So what's going to be in a node of our quadtree? Bucket. Yep. So there's I'd say maybe a bucket. Yeah. So we'll say it's like an array, but it could be empty, right? So for the leaf nodes, we'll just make space for it, for the internal nodes, we'll make space for it, but we won't use it. So bucket question mark. Okay. And then what else do we need? We need 4 children. All right, so we have node, pointers for the northeast, northwest, southeast, southwest. Just a note, if you try to write this in C or C++, this is wrong. This is not what you want. You need the stars for each one of these. So if you're trying to transcribe this later on, the C pointer declaration syntax will irritate you. All right, so that's what's in a node. So let's talk about how we build one of these quadtrees from some points. So what do we do? I just have these points, and somehow I want to turn it into that picture. So I have a tree structure, and what programming paradigm do I probably want to make use of? Recursion, right? I probably want recursion. Right? If I'm doing recursion, I probably want a base case. So what's kind of our base case here when I stop making trees? When I have a small number of points, what should I do? Yeah, so if I have a small number of points, I have a leaf node, I have a bucket, right? So points, dot size is small, right? Return new node out of the points. So this would be, bucket. Actually, yeah. Okay. So if I have a small number of points, cool. I have a leaf node, and we're done here. All right. How about if I have a bunch of points? What do I need to do? I need to recurse, right? So so when I recurse, I'm making a new quadtree, right? How many new quadtrees do I want to make? I'm going to make 4 new quadtrees, right? And which points do I want to use for each one of those quadtrees? So I need to split up my points into the four regions, right? And then I need to make a new quadtree out of each one of those, and then those are my children, right? So I need to divide my points. Right. And then I need to make 4 quadtrees. Right. And then I'm going to return a node with those 4 quadtrees as my children. Cool. Does that kind of make sense? Yeah.
The dividing of the points, I guess it's not completely clear to me how you know ahead of time how many points are in the array.
You don't. Yeah, you don't know ahead of time. So one thing you can do, so you can either just like make a list for each one. If you want to like optimize and be efficient, you can start with your original list and you can just sort it. So you like sort by X and sort by Y in the 2 halves, so that like you're not allocating any new memory. You're just like organizing it so that like the section that you need is in the right spot. But yeah, you don't know how big any of the children will be ahead of time. All right. So this is making a quadtree. Any questions about that? So it's pretty, I mean, it's a little bit more complicated. You know, dividing the points is a little bit more complicated, but not crazy hard. But it's pretty beautiful little recursive algorithm for doing this. Yeah.
It feels like it would be somewhat expensive to create our initial like bucket structure. Is this something that is it valuable to do if you're only going to interact with the data set once? Or
if you're going to do, yeah, if you only have to do one query, you should just look through all the points. Because every data structure we talk about is going to be more expensive to build. If you're doing multiple queries, then you need to do something like this.
Yeah, it's a bad like upfront cost, but it saves you a lot of time.
Yep. Mm-hmm. Yeah. And then there's all of these are going to be sort of n log n-ish type things, or maybe n log n kind of stuff. Yeah, maybe let's think about the runtime for this, because it's maybe not obvious.
It feels like it would depend on data to some degree.
Yeah, so it's going to be data dependent. Here, when we're doing this division, are we going to have to look at all the points? Right. Yeah. So for kind of each level, there's like we have to look at all the points of that level. So this is kind of like a n times height sort of thing, but it's not obvious because we have these early outs here when we hit the threshold. So I think this is kind of a tricky thing to do a good analysis on. But yeah, I would say probably it's somewhere between n and n log n. But I'd say closer to n, but it's tricky to. I think doing a precise analysis would be pretty tricky. So this is Quadtree building it. So we built this data structure. I have a really nice picture. Is this going to speed up our queries? So we really hope so. So let's maybe let's try to think about the range query, and then we'll talk about the Knn query, which is closely related, but just a little bit of a tweak. So, if I want to do a range query, let's say I want to look at all the points in this circle. I'm going to have to Yeah, how am I going to go about this?
Looks like you'd have to find which of the four quadrants it's in, and then go deeper potentially, and then go deeper.
Well, so if we look at this, actually, it's worse than that. I'm in, so if I'm looking at this square, it's actually in 2 of the quadrants. So it might be in multiple quadrants. But that's actually, the key insight is that it might not be in all of the quadrants. Okay. So so where do I have to start my kind of process?
Looks like at the top of the tree.
So I have to start at the root, right? That's kind of my entry point, right? And then from the root, I can look at the children of the root. Right? And do I have to look at all of the children of the root? No, right? So in this case, which children of the root can I ignore? I can ignore all 3 of these, right? And how do I know that I could ignore them all?
I have one that's like appropriate sizes from the corner, all that is in there, or that's something different for.
Yeah, Jordan, you.
Well, you know that the leaf node that you're going to has at least K. I don't know about that. I'm not just question, but you at least know that like there's elements you need in that section.
I don't actually.
Oh, you don't?
So here, so this is a range query. I don't know how many nodes or how many points I'm going to get back.
Okay.
I just know I want everything in this circle.
Okay. Yeah.
And that's actually what makes the next, when we are doing KNN, is hard because I don't know how many points are going to be in here. So looking at this picture, everybody said we don't need to look at any of these 3. How did you know that? We're not, the points right now, we don't even care about the points. The points didn't tell you you could ignore these 3. What told you you could ignore these 3? The circle, right? The circle didn't intersect any of these boxes, right? So we know that there's no way there are points in here that are inside of the circle because the circle doesn't go in here. So when we do our range query, basically anytime we're going to go into a node that doesn't overlap with our circle, we just don't go there. Yeah?
Maybe this is obvious, but is that just from the math that you're doing? You're dividing it into the quadrants ahead of time? And then saying,
Yeah, so in this case, it's pretty easy. We know where these 2 lines are, right? So for the circle to cross those lines, we just look at like this position minus the radius, this position plus the radius. And if there's no part of the circle that's across that line, we just don't deal with it. Another way you can think about it is, that's kind of handy for some of the other data structures, is basically you find the closest point on the box to the point we're looking at, and then look at the distance to here. So in this case, for this box, right, the closest point to the query point is this one on the edge, right? And then I look at the distance there, and the distance is greater, so I know none of the points in this box can be closer, so none of the points in here could be inside the circle. That's another way of thinking about it. So yeah, like being able to think about the closest point in a box to another point. It's either going to be, so for here, for this big rectangle, or this square, what is the closest point in here to here? This is like kind of a trick question. So it's like the point itself, right? So if my point is inside that box, the closest point is that point. It could also be on an edge or a corner if I'm outside. And it's actually really easy to figure out what that closest point is. Cool. And so let's write out our range query. And I guess this also takes an n. N doesn't intersect our circle. We're done with it. Okay. So there's no, we don't need to look any further. We don't care about the children. We don't care about the bucket. Nothing. Don't care. Right? If N is a leaf, what should we do? So the leaf node, we just need to look at the points in the bucket. Right? Look at, we need to look in the bucket. Right? If we're an internal node, what do we do? So we're internal node, right? We just look at all 4 of our children. Right? So we just add up, or we recurse to all of our children. So that's the basic idea. Is this an improvement over the like no structure data structure?
Doesn't seem like it, because when you're trying to find intersection points, so going to the closest point in the quadrant, seems like to find the closest point in the previous quadrant, you have to look at the point.
So when I said that, I don't mean the closest data point that we have. I mean the closest like point in space. So actually, that only depends on the size of the box.
I see.
So that's really fast to figure out. So it's either if my point is in the box, it's that point. Otherwise, it's an edge or a corner. And so that's really fast to do. Yeah. So this check is really fast. Right? This is basically what we were already doing, but we have the advantage of knowing that our buckets are small because we constructed our tree to keep our buckets small. Yeah, we might have to look at a lot of children. We might not. What does the performance of this depend on? I think it's pretty obvious that it's highly variable, right? So like, if we're hitting this case a lot, the performance is going to be awesome. Right? If we're doing these 2 things a lot, it's not going to be so great. So what does the performance depend on? Yeah, it depends basically like how many quadrants does my circle overlap. So they could depend on specifically where my circle is. Right? If my circle happens to just be in an area where there's a whole bunch of little boxes, right, I have to recurse really far. Especially like if I was like here and this was subdivided really small and this was subdivided really small, like I might have to look at a lot of stuff. If my radius was really big, right, I'm gonna have to look at a lot of little boxes, and there's not really much that could be done about that, but I'm adding a little bit of extra overhead doing this tree traversal stuff as opposed to just like scanning through a list. In general, this is an improvement. So how do we think this compares to the like uniform grid that we just talked about? So when would it be better than the basic bucket approach that we talked about? Yeah, if I have to use less quadrants, right? So when, like, how would my data? What would my data look like to make that happen? So this is a pretty good example. If my data is clumped, right? The quadtree can be a big win because a big areas of the space are, these huge buckets, like huge spatial buckets with not that many points in them. Right, so I'm not storing a whole bunch of buckets to keep track of like 5 points. Right, I have like one huge quadrant with 5 points in it. Right, if I need to look there, it's going to be fast. Right, and then where I need to be much more finer grained, right, this tree structure helps me out there. So for data that's like non-uniformly distributed, this can be a big one. This is my my range query. Any thoughts on how I can do KNN with this? So what's the dumb way to do KNN? Range query and just keep bumping up my R. And that's actually kind of what the actual optimized KNN version does. Except that actually the R shrinks. Okay. So I'm not going to write out the pseudocode, I'm just going to talk about kind of the intuition. But what we do is basically we just start going through the tree. And to start with, we're looking for any point that could be any distance away from our query point. Because we don't know how far away the k closest are going to be. Right? So we have to just kind of be stuck with any points. Okay. So here we're kind of starting with r equals infinity, and we're searching. Okay. So if r is infinity, basically, we're never going to cull. We're never going to like skip over, leave any nodes because like they could all be there. Okay. As we go, we're going to keep track of the k closest points. Okay. Once we get k of them, now we can start being really selective. Okay? So the farthest away of the k best points that we've seen so far, that gives us a circle. Right? We know that any points that are the k nearest neighbors have to be at least as close as the ones I've seen so far. Right? So at some point, right, if I'm going through here, like if I'm looking for the KNN around this point, right? If I say I search this quadrant first, right? Once I see this point, I now know that like the k nearest neighbors have to be within that circle. Okay? So my R starts to shrink. Okay? And so if I find a new point that's closer, so I say here, okay, well now my circle's even smaller. And my circle is actually going to shrink down until I get like really tight on the k nearest neighbors. So actually it works. The general outline of the algorithm is the same, but my radius is actually shrinking as I find better and closer points. I can shrink, and toward the end I can start culling all these leaves as I zero in. So that's kind of an outline of the KNN algorithm. It's more efficient than just doing a bunch of range queries, right? I start with a wide net, and then I just kind of zero in using the same strategy that I do with the range query, but just keeping track of the k closest that I've seen as I go. That kind of makes sense.
How do you narrow it down to smaller range?
So each time I look at a point, if it is closer than the farthest of the best I've seen, then I stick it in there. And the one that was the farthest of the k has been thrown out. And the one that is now the farthest of the k is slightly closer than that one. And I know that any of the best k overall have to be closer than that. So each time I put a new nearest neighbor into my list of the best so far, I actually shrink the search area where the best overall could be. So if I'm looking for, let's say k is 1, right? I go out here, this is the best I've seen. I know I can ignore any point that's further than this. And then let's say I find one here, I know I can ignore any point that's farther than that. Right? And as I find better and better points, I can start culling more and more of the leaves I haven't looked at yet. Or more and more of the nodes I haven't looked at.
Feels like it should take a really long
It could, yep. In practice, it seems to work pretty well. Yeah. So it kind of depends on the luck of, or the choice of ordering that I visit stuff in. But just kind of on average, it works pretty well.
How do you know, I guess, which ones, to omit?
So when you find a point that's closer than the farthest that you've seen so far, the farthest good one you've seen, you just kick that one out and insert the new one in. Kind of, you keep that list sorted, and then the farthest away one you just pop out. In fact, you don't need to sort it. You need to, I don't know if I think we've talked about this data structure. We need to be able to kick out the biggest element and look at the biggest element efficiently. And that's really the only operation we need. What data structure should we use for that? Priority queue, which is, that's kind of the more abstract type. You may remember how that's implemented, the data structure there. It's kind of a tree. It's usually implicitly a tree. So the stack doesn't have ordering based on the values. It's called a heap. We talked about heaps. So this is a max heap, right? We need to know the one that's farthest away in our list. We need to be able to kick that one out, stick a new one in. We don't really need it to be sorted. So yeah, I can use the max heap there. Cool. All right, so Quadtree, pretty neat data structure. Visually, it looks really cool, I think. It's like, if you like watch kind of like hacker stuff, like this would be like a cool thing to be up on my screen while I'm like hacking into whatever. So this is a really interesting data structure. All right. So yeah, this is good for data that's not uniformly distributed. Again, it's more complicated than there's aspects of it that are more complicated than the buckets. It's got this nice recursive structure. But it does not scale to many dimensions very well. Other Quadtree questions? Okay, so we're going to talk about one more data structure, which does work really well in a whole bunch of dimensions. And it is also a tree structure, but it's a binary tree. And it's basically a generalization of binary search trees to multidimensional data. Okay. So we talked about yesterday how one thing we could do is just like sort our data and why that may or may not be helpful, right? So I might have, so if I sort based on like X, I might have points, my closest points might be pretty far away in X, but close in Y. So if I sort by X, that doesn't really help me find stuff. I could use it to like narrow down my search maybe or something, but you can imagine as I add more and more dimensions, sorting by one of them is probably not going to help me quickly find the points I want. I could try like sorting by each different dimension and like looking at all of these lists or something. So I could have like one list sorted by X, one sorted by Y, one sorted by Z, and then like try to use that to somehow help me search. That also doesn't work super well. Okay. So what we're going to do is we're going to start by kind of sorting by X so we can do a binary search in the X direction. Okay. So if I want to like throw away half of the points because they're too far away in the X direction, what do I need to know? basically need to know, I want to like split my data into two halves. I don't really need to sort it. I just want to be able to know like kind of which half I care about. So what do I need to know for that? Which element is going to tell me where the middle is? The median. Okay. So I could find the point with the median x coordinate. Okay. And this will split my data in half. Right? Okay. I could do this, if I wanted a binary search in x, right, so I could kind of keep doing this. And I'm going to have all these little slices, right? And because the slices are like infinitely tall, then things that are in the same slice might not actually be that close compared to things in nearby slices. But I can change the way that I do my cutting. Okay? So the next time I want to divide, instead of dividing based on x and making another vertical slice, I'm going to cut this way. Okay. And at each level, I'm going to alternate my cutting directions. And I might get something that looks like that. So what I'm doing here is I'm just finding the median in alternating dimensions, and I'm using that to split, so I can do a binary kind of search. But I'm alternating the coordinate at each level. That kind of makes sense. So this is called a KD tree, okay. And the nodes, I have one different type of node for each dimension. At each node, I store 1 point, which is my splitting point. Okay. And then I have exactly 2 children that are actually a different type of node. Right? So if I'm an X node, my children are actually Y nodes. Right? If I split this way, my children are going to split this way. Okay. So I'm going to write this out in kind of sort of C++. I'm going to have 2 children of the next level's nodes that are my left and right child. Okay. Yeah.
So if we are just finding the median each dividing, then they will always be uniform, but this is not uniform.
So the median will not be uniform because the median depends on the actual values I had. If it were the mean, then I would get something uniform. Then it would look basically be a quadtree, basically, but with like twice the number of levels. Since I'm looking at the median, it's data dependent, and so things are not, the boxes are not all the same size, but the boxes at each level contain about the same number of points. Another kind of weird thing about the KD tree is that all of the boxes along the outside are infinite. Right, so this box goes down to infinity. There's no points out here, but and this box also goes out to infinity in these directions. So this is a pretty cool data structure. Let's talk about doing like a range query over here. What are doing a range query here look like? Actually looks remarkably similar to this. Right, the implementation is the pseudocode that as I've written it is very, very similar. Okay? If my node doesn't intersect the circle, then I can ignore it and all its children. Right? And if it does, then I look at the point in this node and then look at my children potentially. Okay? So here, so this is my root. This is my root dot left and my root dot right. Okay. So my root dot right basically is this whole half plane, this whole half side of the world. Right? And then my root left is this whole half of the world. Right? So this is a little bit weirder from the quadtree because we're dealing with kind of infinite stuff. But for the purposes of like determining whether or not the circle overlaps, we only have to look at the finite parts. So again, this is where thinking about it in terms of like the closest point in that area to my query points is kind of a useful thing. So for here, like for the right side of my tree, the closest point in this area to this query point would be this guy right here, which is outside of the circle, so I can totally ignore the whole right half of the tree when I'm doing this search. Okay.
So, I mean, this seems a lot more elegant to me than the quadtree, but at what point would you, I guess when you're choosing a data structure, when did you choose one or the other?
That was a good question. I think that KD trees tend to be more common. I don't know that I have a good answer for when quadtrees would be better. Yeah, I guess, so if you care about the volumes being uniform, then the quadtree would be better. So here we're going to get this really irregular shape. If you cared about the regular structure, then the quadtree would be good. So they get used for like simulation, where you're like trying to break up space into cells so you can do some sort of physics computation or whatever. In those cases, quadtrees can be more useful because there's like regular structure. Yeah, like KD trees are really popular. Other questions? Yeah.
This question makes sense. So before, when we were kind of drawing our quadrants based on how many points are in a given space, we have this very uniform look of quadrants being divided. Does this formation show anything else about the data by looking at all these different medians and all these different places? Can that point towards anything?
Yeah, it's like, so the visualization of the quadtree would be useful. The visualization of the KD tree. Good question. So the KD tree is going to be balanced. So the quadtree, because it's based on the space and on the data, might be really unbalanced. So we had parts where there was like the root had 3 leaf nodes, and then the one internal node like went down pretty far. KD tree is going to be balanced. You might learn something by seeing like the size of the regions. That might tell you something about the spacing. Yeah, that's a good question. I think the balancing maybe kind of hides, or it transforms the information into a different way. They both kind of have some information about the density, but it's sort of presented in a different way. So I think we'll stop there for today. We'll talk about the pseudocode for the KD tree tomorrow. And yeah, so how many people are like actually interested by stuff like this? Just curious. I think the data structures where there's like a geometric component, I think are just really cool. So that's why I'm forcing you to endure them. Also, so the assignment we're going to do with these, you're going to implement them to get So it'll give you practice writing kind of tricky tree traversal code, all that sort of stuff. And it's also going to give us some interesting data sets to analyze. So we're going to look at the runtimes of these depending on K and N. And we can use our newfound skill with regression and plotting and all that stuff to actually analyze and try to compare these and see which one of these work best when, that kind of stuff. So that assignment will come out next week. Yeah. Right. I'll see you all tomorrow.
So I can see.